This is an English version of a presentation I gave in February 2025 at the University of Milano Bicocca after an invitation by Professor Emilio Padoa Schioppa. I recorded it afterwards, and here it is. So what was I talking about this presentation? It was for students, high school students, so I had to limit, of course, the details that I could show, but I tried to give a presentation which was sufficiently in depth to understand some mechanisms of how we humans see the future, how we deal with it, and how we try to understand what the future is. And I started by showing this book that it's the Italian version of a famous study, which you probably know with the name of The Limits to Growth. And this is in Italian, Limiti dello sviluppo. And this book, students had never heard of it, of course, but it was a real important book because it set a standard. It was the first time that we could project in the future the trends of a complex system, in this case, the system, the socio-economic system, global, the humankind as a whole, into the future using a program which had something in common with the concept of artificial intelligence, in the sense that it was a program that could examine all the parameters together without all the biases which are typical of the human mind. We humans are made in a different way. When we have a complex multi-parameter system, we tend to try to find shortcuts and see if we can understand the system just by looking at one thing of the many that are part of this system. That's, of course, sometimes it works, but sometimes it will lead you to very bad mistakes. Instead, if you can use a computer which is not human, obviously, it doesn't have preferences, it doesn't have political ideas, and no preconceived ideas, so it keeps growing, keep doing things, and the result is this diagram that you see here that illustrates some of the main parameters of the economic system, which goes up and then goes down, and so it is sort of pessimistic. Indeed, it was badly criticized, defamed, demonized, and eventually consigned to the dustbin of wrong scientific theories. But it was not so simple. It was a political reaction to a scientific study. And the two things, politics and science, don't match very well with each other. So what I was trying to do was to match these two things, to try to explain what is the future. And I started from the beginning. Why do we want to predict the future? Why are we so interested about the future? When did our ancestors start worrying about the future? Because it's a story. I mean, that starts with civilization. When people started to try to find regularities, what we call laws, universal laws. Why are there universal laws? The law of gravity, the law of thermodynamics, they seem to be valid universally. But why is that? Of course, the ancient didn't have these ideas, but they had some feeling, some understanding that the universe is somewhat predictable. It follows patterns which can somehow be understood. And they added to this kind of understanding the idea that gods were somehow moving, generating the universe. But carefully, our ancestors were not stupid. Their vision was very the best that they could have at the time. It was articulated, it was smart, and they tried to use these views in order to understand as much as possible the future. And well, let me show you a few things that I hope will convince you that they were doing things under many respects similar to what we have been doing in our times. So let me start. I will show this image here to start, which is the Pythoness or the Pythia or the prophetess of the temple of Delphi in very ancient times. We are talking about of a few centuries before our era. Who was the Pythoness? There was this lady, young lady, who would sit on top of this, you can see here, sort of pit, something where this was said that long time ago, a deity, a sort of some kind of god, a snake god, died, and it's still there. The body, the corpse of this god is still down there, and is slowly decomposing and emitting fumes that you can see in this image. And the poor lady was sniffing these fumes and going a little out of her mind, and starts prophesying, saying strange things. But really, it was not so silly as it looks to us. Think about that. The temple of Delphi didn't work just with the Pythoness. The Pythoness was not an isolated figure. There was a whole priesthood of people around the temple, and this priesthood would collect the questions that were asked by the people who would go to the temple to ask about the future. And that meant that the temple had some capability of information processing, which means assume that a king goes to see the Pythia and asks, oh, if I attack my neighbor, will I win? And the Pythia would say something that could be interpreted in two different ways, but the priests would know that that king had at least the intention, the idea of attacking his neighbors. Now, imagine that the king of the neighborhood were to come here and say, we know that your neighbor is a bit aggressive. So you had a certain logic, not so much different from the way we do things with our artificial intelligence programs that we use. Now they have a large database, much larger than anything that the Pythia could have, but they extract from this big database data which can help us to understand the future. And but this depends on many things, and it depends on what kind of range of the future and how you see the future coming down from because nobody can do experiments with the future. Just one thing that allows us to understand the future is the capability that we have of measuring time. And before I go into the details, let me show you another image that I show to the students to interest them a little bit, because you have to ask questions, you have to do these kind of things, and say, what do you see in this image that is curious? You can see it's an image that comes from the year 350 of our era, which means the late Roman Empire. And it represents the wedding of Peleus and Thetis, which is a story of long ago, which is not the point we are interested in here. But there is an element, a detail in this image, which was never shown before, and which is the key of the whole universe. And I asked to the students, can you identify it? They could not. It is not easy. From home you can try to identify it, but I made a little show of showing them, okay, inside this box there is the secret of the universe, and that's what is that? And just to show you what it was, wow, take some work, and you see what it is. Hourglass. You can see it, you know what it is. Can you see it in the image here? There it is. Hourglass. This is the first known image of a sand glass of hourglass in history. Maybe it was older than that, but at least in 350 AD, the sand glasses existed. They knew it, and this sand glass, of course, tell us that they had already developed capability of measuring time. And the sand glass is a special machine which measures time in a linear way. proportional. The time passes proportionally to the flow of sand grains from the upper part to the lower part. It's a curious peculiarity of this object that it is linear, really. It is constant. The flow is constant, which is strange. This object that you see here is maybe a water glass, which had the characteristic that it was not linear. At the time of water glasses, the hours of the day were not all of the same length. It depended on different things, but they started to be very scientific, very linear, very precise. This one was 15 minutes, and you know that this is fixed time span. But the point is now that there is something interesting here, which is this machine is linear from here to here. But here, what does it happen here? And it took a couple of millennia before people start looking at what happens down here and say, well, what? How can you describe the piling up of the sand at the bottom? And let me show you how it works. This machine that I recorded the falling of the grains of sand, and you notice something. It grows up and it gathers height, and then it goes down through avalanches which are usually of different size and happen at different intervals. And that was a work that the first person, I think, or group of persons who started looking at that. They came from a completely different field of electronics, but they started looking, well, what is this? Why can't we describe it? And one scientist whose name was Pierre Beck, he was a Danish student, a Danish researcher at the Brookhaven laboratory near New York, and he started asking questions. And once you ask questions, you learn something, and you learn how this phenomenon occurs. And it came out that he could make a model. He could not find an equation of the sand glass. That's not possible. This is a typical complex phenomenon because you have many elements interacting with each other. Every sand glass interacts with several sand grains around, and so the behavior is complex. It's non-linear. It cannot be described by simple laws, but only statistically, and it has to do with the way the universe works, or nature works. This book was written by Per Bach, as you can see, a book written in the 1980s, and he laid down the foundation for a new science called the science of self-organized criticality. And he made models of the hourglass and various equations and things, but the result finally is that nature really works this way. Works like the bottom of sand glass, and it goes up and down, and there is a logic in this movement of waves, but you can never predict when a avalanche will occur, which is, this happens in real life. So let's see, that's the way the world works. It's a metaphor of the way the world works. It's about the waves of the sea. They come with a certain regularity, but you can never be exactly sure of how high or how frequent the new waves will be. And this is something that Bach showed on the cover of his book, with sand dunes in the desert. Waves are really very common at this point. To make the students happy, I show them a little catastrophic movie. Let me show it to you. And that's a lot of fun, as you can see. It's the characteristic of these big waves, tsunamis, is that they're unexpected. As you saw in the movie, people were staying in the beach, they didn't expect this thing to crash on them. But it happens in the real world. When you have phenomena, critical phenomena, you can never know for sure when they will happen and how they will happen. What you can say is that they will take the form of a wave, typically. And sometimes they're quite damaging, not always, not necessarily, but that's typical. So question is, how do you describe this? The first thing, you have to visualize these waves. In order to understand something, you have to find a way to visualize it. In physics, normally you have a way to visualizing, to understand, to encode these things. You use equations. Here you cannot use equation, but you use typically graphs. They show you that the wave has a certain logic, a certain repeatability. Already at the time of Seneca, the philosopher, they knew this, but they could only express in words. You see, Seneca, all what he can say is that increases have sluggish growth, but the way to ruin is rapid. But he could not write down equations, but we can, and he could not write an equation of this curve. But even if you cannot, already in the 1940s, the 1840s, mid-19th century, people could visualize these curves as these bell-shaped waves of things. This is an epidemic, the cholera epidemics of 1849 in New York. This image was shown in the New York Post of those times. Note how big is the caption of this figure, because this is the first time people saw, most people saw one of these curves, an epidemiologic curve, because they had to explain it in great detail. At that time, people didn't understand Cartesian graphs. Now it's not changed so much, because still most people cannot understand a Cartesian graph, one with just the time here and the intensity of something here. It took a few millennia to arrive to be able to show this, but then people saw that it is very general. It describes a lot of phenomena. And it was first discovered with epidemics. And now we should know that, because in 2020 with the COVID, it had the same behavior. And I have to say that even at that time, a lot of people did not understand this, and they would say, well, we will all die because we'll keep growing to infinity. No, it doesn't happen. It is a typical, an evident, a classic, a clear complex system in which you have something that moves under the effect of energy potential, just like the sand grains move down as an effect of the gravitational potential. The viruses that attack your body or another creature's body, they act to dissipate a biological potential. They have this capability of attacking your cells, reproduce, and then grow and attacking more cells. So it is not linear, it grows because you move from one victim to another. But then the number of targets is limited. So you have this behavior. Initially they grow very fast because there are a lot of targets. But as people become immune or die, maybe, the number of targets goes down. So the curve must slow down, and eventually there will not be enough targets to keep the virus growing. And this is very, very general. It applies to a lot of phenomena, not just epidemics, but back in the 1920s, the first equations that could describe this system were developed by some mathematicians at the time. And this is called the SIR, susceptible, infected, recovered. Notice that there is not a single equation here. This is a system of two coupled differential equations. And it gives you this bell-shaped curve. Now, I'm not going to go into the details of this, but it is a mathematical version of what I told you. Grow, slow down, stabilize, go down. It is something that the Seneca had understood very well at this time. I could not express it with differential equations, but that's the idea. And the interesting part here is that you can take these equations, apply to a lot of phenomena in biology, for instance, but also in economics, but in many other fields. And this is what I started with, showing you these equations now a little on a larger scale. This is an epidemic, a worldwide pandemic of humans growing and expanding into the ecosystem. Just like viruses tend to use the resources they have from the viewpoint of a virus, we are resources. From our viewpoint, resources are metals, are energy, oil, gas, coal, all sorts of minerals that we extract from the ground. And the calculation of this scenario was made using that kind of equation, more complex than that, but the nucleus was there. And you see, it works like a virus expanding. This is the violet curve, is the human population, goes up and then it goes down, but it has this behavior which is created by subsystems like the industrial production, this green thing here, and the agricultural production, the dark brown here. And there is an extra parameter which didn't exist in pandemics, in epidemiology. There is the pollution. Pollution is this curve here, which also has the effect of weighing down the system. The system has difficulties in growing, first of all, because it gradually runs down of resources, and also because it is bitten down by the pollution it creates while growing. And it could be applied to global warming, to microplastic, heavy metals, and every kind of pollution that we have to spend money to abate if we can, because it doesn't always work. And you see how the system depends on resources, the red line, which they never run out completely. But the system, at some moment, the system is not able anymore to exploit them. And this is the fundamental point. The fundamental point that makes this book a little bit deviant for the economists, because it goes against the commonly stated parameter that we can keep growing forever, which is a little bit difficult on a finite planet, and the reason why it was demonized, etc. But it is not. You have to take a balanced position. This is not a prediction. It was never said to be a prophecy. Just like at the time of the Pythoness, she was saying things that could be interpreted in various ways. This book had several possible predictions, not just that one. They had many different ones. And because none of these scenarios was supposed to be a prediction, it depends on what you do. And looking at this book is the equivalent of going to the Pythoness and asking, what is going to happen if I do this? And if you do this, you have this or another one, depending if you do another thing. It depends on you. The future is something open. You keep doing the things you've been doing up to now, then this is the result. You grow and collapse. And that's unavoidable unless you change the way you do things, which is possible. Why not? You have to be more careful. You have to limit a little bit what you do. You don't want to grow all the time as fast as possible. You want to use better technology which do not pollute, because otherwise you will be destroyed by pollution, but it is possible to keep growing a little bit less, not so fast, and then have a lower decline, or maybe you can stabilize the system. The ideal thing, but I don't think we will be able to do, but it is not impossible, is to stabilize the system. You want to arrive to a system which you don't have this roller coaster up and down. You don't want to be hit by a tsunami. You want to stabilize. You want to have something like a feng shui situation, as you can see here, and that's eventually something that complex systems tend to attain by themselves. But it takes time and several oscillations, which may be rather painful. So these ideas, these concepts of how the complex system behave, or how time is understood to move in a certain direction, how our actions affect what happens. So all these things that cannot be used to predict the future, but can be used to be prepared for it. And I hope you found this presentation interesting, and thank you for your attention.